And very recently, some researchers have tried to connect the kernel trick and neural network. Of course, neural networks is kind of dominant algorithm very recently. So in most of application, people love to use neural networks instead of classical machine learning technique like Gaussian process, linear regression, or support vector machine. So I think from 2012, 2013, uh, most of papers in machine learning use deep learning architecture and neural networks. But the problem was nobody can explain why neural networks works very well clearly. Okay, so some theoretical computer scientists and statistical physicists and information theorists, many people try to understand neural networks theoretically, and kernel method was one of them. And this paper is very interesting, and many followed work also very interesting, and called neural tangent kernel convergence and generalization in neural network. Here they claim they consider a fully connected neural network with infinite widths. So here infinite widths means essentially when you design a neural network, each layer. So first of all, neural network is layer-wise structure. It consists of many layers, and each layer consists of neurons. There are many different elements in one single layer, and the number of neurons in one layer is called width. So when we make infinitely many neurons per each layer, in the infinite width limit, the neural network converges to a deterministic kernel and stays constant during training. Okay, when we have infinitely many neurons, the neural networks is kind of kernel. And we can explain the neural network using kernel method. So that is neural tangent kernel. So why tangent is in the name? I will explain. Okay, so from the Taylor expansion, we know this. So when we control the parameter theta very little bit, very tiny amount from the original theta 0, we can approximate the function using this tangent function. Okay, we can approximate any function using first order polynomial. The slope comes from the gradient. When this distance, theta minus theta 0, is very tiny. So even this wiggly function, when you zoom in this part, any part, when you zoom in a lot, then the function looks like linear. Okay. Of course, if the function is continuous. So from this property, when we have very tiny update during the learning process, we can always approximate this process using this Taylor expansion. We can approximate the function using this Taylor expansion. And indeed, when we have infinitely many neurons for each layer, from experiment and from theoretically, we can show that the update is very tiny. Every single update is very tiny. So it is good to approximate the original function fx theta. When you consider the function with respect to theta, the parameter, the neural net parameter, it looks like this function is almost follow the tangent function with respect to the theta when you center at the original, the initial parameter theta 0. Okay. Then when you look at this function in view of x, there is very interesting thing. this is kind of feature expansion of x. For any input x, we can define this gradient vector, and the gradient vector is kind of expanded feature map, right? And so this is a kind of x prime, so expanded feature map. And this mapping make our regression task as a linear regression with respect to this expanded feature map. And when you deal with expanded feature map and linear regression, in the previous slide I explained, in that case we can use kernel tree. So what we need to know the function value fx for any new data point, we just need to know the inner product between gradient. When we collect all the inner product between gradient, we can predict any output fx. So the neural net function can be approximated by this tangent function, and this tangent function tells us it looks like this neural net regression problem looks like a linear regression with expanded feature map and feature expansion, and the feature expansion map is the gradient. Okay, and one nice thing of this approach is there are many nice theory for the kernel method, and the kernel method essentially can explain the generalization behavior. So previously it was totally mysterious. Although the neural network have millions of billions of parameters, which is much bigger than the number of training data point, the generalization behavior was very nice. It can not be explained by classical machine learning theory. In classical machine learning theory, when you have such a huge overparameterized model, overfitting always there, and we will suffer from the high generalization gap, high difference between training error and test error. But in practice, people consistently observe that the training and test error difference is not huge, even with such huge overparameterized model. And this approach, the kernel method, partially explain why such huge parameter still have very nice generalization behavior, which is because the neural net can be approximated by a tangent kernel, a kernel method, and kernel methods usually have a very nice convergence behavior and very nice generalization behavior. That is one nice thing of neural tangent kernel. It gives us some hint of why neural net works very well. And also, some people just utilize this fact to design a new kernel and new kernel method. So instead of using IVF kernel in the previous examples, just define a new kernel using a very wide neural network. Bring a very wide neural network and compute the kernel function using the neural network. That's also very interesting approach to many applications.